Hello, welcome to Quadratic Equations Lesson 3. During this lesson, we will study how to solve quadratic equations using the quadratic formula. If the quadratic trinomial ax squared plus bx plus c is not factorable, to solve the quadratic equation ax squared plus bx plus c equals 0, apply the quadratic formula. X equals minus b plus minus square root of b squared minus 4ac divided by 2a. Of course, you can apply this formula also in the case when the quadratic trinomial ax squared plus bx plus c is factorable. But in this case, it is easier to solve the quadratic equation by factoring. The expression b squared minus 4ac, which stands under the radical sign, is called the discriminant. So the discriminant is b squared minus 4ac. If the discriminant is a perfect square, it means that it is a number like 9, 16, 25, 144, then the roots of the quadratic equation are rational. It means they are fractions or integers. In this case, it is easier to solve the quadratic equation by factoring. But if the discriminant b squared minus 4ac is not a perfect square, like numbers 6, 8, 12, 24, 17, 7, then you cannot solve the quadratic equation by factoring, and it's better to apply the quadratic formula. Vieta's formulas relate the coefficients of the quadratic equation ax squared plus bx plus c equals 0 to the sum and the product of its roots. These formulas state that the sum of the roots of the quadratic equation ax squared plus bx plus c equals 0 equals minus b over a, second coefficient with opposite sign divided by the first coefficient, and the product of the roots equals constant term c divided by the first coefficient a. These formulas were named after the outstanding French mathematician Franciscus Vieta, who developed these formulas. We can apply Vieta's formulas to check the solution of a quadratic equation. Example 1. Find in radical form the roots of the quadratic equation x squared minus 6x plus 7 equals 0. In this case, a equals 1, it is coefficient of x squared, b is negative 6, coefficient of x, and c is constant term, c is 7. We apply the quadratic formula and substitute these values of a, b, and c into this formula. We get the following expression. Let us evaluate the discriminant. Minus 6 squared is 36, and minus 4 times 1 times 7 is negative 28. 36 minus 28 is 8. But 8 is the product of 4 and 2. Therefore, instead of square root of 8, we can write 2 square root of 2. Now we divide each term of the numerator by 2. 6 divided by 2 is 3. 2 square root of 2 divided by 2 is square root of 2. Therefore, the given quadratic equation has two roots. One root is 3 minus square root of 2, and the other root is 3 plus square root of 2. Let us check the solutions. Let us find the sum of the roots. we have to add 3 minus square root of 2 and 3 plus square root of 2. Minus square root of 2 and plus square root of 2 cross out. 3 plus 3 is 6. And 6 equals minus b over a. Because minus b is minus 6 is plus 6. Divide by 1 would be 6. The product of the roots x1 times x2. We must multiply 3 minus square root of 2 times 3 plus square root of 2. In this case, it's better not just to expand the brackets, usual way when you FOIL it, first times first, first times second, second times first, second times second, but to apply a formula, which is called difference of squares. So it is the square of 3 minus the square of square root of 2. 3 squared minus square root of 2 squared. 3 squared is 9. Square root of 2 squared is 2. 9 minus 2 is 7, which equals 2c over a, because c is 7 and a is 1. So we checked that the sum of the roots equals minus b over a, and the product of the roots equals c over a. Therefore, we solved the quadratic equation correctly. Example 2. Solve for x. 2x squared minus 4x minus 3 equals 0. In this case, a is 2, b is minus 4, and c is negative 3. We substitute these values into the quadratic formula and we get this expression. Check it, please. Let us evaluate the discriminant. Minus 4 squared is 16, minus 4 times 2 times negative 3 is positive 24. 16 plus 24 is 40, but 40 is the product of 4 and 10, and square root of 4 is 2. Therefore, instead of square root of 40, we can write 2 square root of 10. Now we can reduce this fraction by 2. We divide each term of the numerator by 2 and denominator we also divide by 2. 4 divided by 2 is 2, 2 square root of 10 divided by 2 is square root of 10, and 4 divided by 2 is 2. And we get the roots of the equation in simplest form. This equation has two real roots, 2 minus square root of 10 over 2 and 2 plus square root of 10 over 2. Let us check the roots using Vieta's formulas. The sum of the roots, 2 minus square root of 10 over 2 plus 2 plus square root of 10 over 2. As usual, minus square root of 10 and plus square root of 10 cross out. 2 plus 2 is 4, and common denominator is 2. So the sum of the roots is 4 over 2, which is minus b. Minus b is 4 over a is 2. The product of the roots, we have to multiply these two expressions. We multiply the denominators, 2 times 2 is 4, and when we multiply the numerators, we apply the formula difference of squares, and we get 2 squared minus square root of 10 squared, which is 4 minus 10 equals negative 6. So we get negative 6 over 4, then we reduce this fraction by 2, and we get minus 3 over 2, which equals to c over a. c is minus 3 and a is 2. Therefore, we checked that the sum of the roots is minus b over a, and the product of the roots is c over a. Therefore, we solved the quadratic equation correctly. Example 3. The sum of the zeros of the function y equals 3x squared minus 6x minus 4 is, and you have 5 possible answers. You have to choose the right one. The right choice would be D. And in order to answer this question, we need not find the zeros of the function. You can do this way, but it's better to apply Vieta's formulas. You know that the sum of the roots, the sum of the zeros of the quadratic function equals minus b over a. In our case, b is negative 6. I substitute instead of b negative 6, and a is 3. Minus minus, it would be plus, and 6 divided by 3 gives 2. Therefore, the sum of the roots equals 2. This is the end of this lesson. Thank you very much for participation. This was Vladimir Luzgin. Goodbye.